Welcome, dear audience, electrochemists, colleagues, and inquisitive scientists. My name is Hector Lara. I welcome you to the webinar on in situ studies of SEI evolution in lithium-ion batteries, morphology, mechanics, and electrochemistry. Formation of a solid electrolyte interface, or SEI, is a contributor to capacity fade over many cycles and clearly an element of great interest for research in lithium battery degradation mechanisms. Today, Drs. Zhang, Huang, and Kumar will be presenting their studies and research on this subject. Dr. Xingcheng is a research engineer at General Motors R&D Center. Prior to joining General Motors, he graduated from University of Kentucky with a PhD in material science and engineering. During his PhD studies, he was working on joint lithium-ion battery projects with General Motors. In the past year, Dr. Zhang focused on characterization and optimization of solid electrolyte interface systems for advanced anodes to improve the cycling stability and cell reliability. Dr. Zhang has more than 30 journal publications and several patent applications. Dr. Teddy Huang is a senior application scientist at Bruker AFM unit. He obtained his PhD degree in physical chemistry from Emory University in 2012. After graduation, he worked at Caltech as a postdoctoral scholar where he investigated the semiconductor metal interfacial structure using AFM nanoelectric measurements. He joined Bruker in 2014 and now leads the team for development of AFM-based electrical and electrochemical applications. As of today, he has published 40 peer-reviewed articles with 1,800 citations and an H-index of 19. Dr. Ravi Kumar is Ravi Kumar is a PhD student in materials engineering at Brown University. He obtained his bachelor's degree from IIT Kanpur, India in 2008. After that, he worked at Tata R&D in India for 3 years before joining Brown. The focus on his PhD thesis is of failure mechanisms of lithium-ion batteries based on both thin film and practical composite architectures. Again, I welcome you, and I'm going to hand it off to Dr. Zhang so he can walk us through his talk and on his results on research. Thank you. Dr. Zhang?
Okay, I'm here. Thank you for the introduction. First of all, I will introduce a little bit about the importance of this topic, which is highly related with automotive applications. On this page, it shows the electrification solutions for the automobiles. It's starting from the light electrification, such as start-stop batteries. With the increase in the capacity of the battery, people start using hybrid electric vehicles, which allows power to be regenerated during the deacceleration. When we have more battery capability, auto industry has introduced a plug-in hybrid electric vehicle, or PHEV. Because there are bigger battery in the system with higher capacity, we can charge and charge the battery, use a plug-in system, so we can have some pure electric driving range. After that, GM introduced the extended range electric vehicle, and Chevy Volt is one representation. The extended range electric vehicle is doing work like this. First, there's a battery driving the vehicles, and for Chevy Volt, it has 53 miles of the battery driving range. And after that, if you drive a longer range, the gasoline will take into the reaction, and they have a power generator there to generate the electricity to power the electric motor. That gives us a total of 420 miles of driving range. And for releasing later this year, I think the production has started for the Chevrolet Bolt, which is a pure electric vehicle. There's no gasoline in the system. The whole the vehicle is based on the electricity, which gives us an EPA estimate of 238 miles per single fully charged. And the Chevy Bolt is the only electric vehicle on the market right now, which are MSRP lower than $40,000, and after a tax incentive, the overall cost is lower than $30,000. So auto industry are very interested in doing the vehicle electrification because the increasing electrification will give us a better fuel efficiency that is related with regulations as well as the climate change. By increasing the electrification, we can have light dependent on the petroleum fumes. On this page, it shows one example of the battery electrode system. Today, most widely used system is in anode is a graphite, which give us a specific capacity of 372 milliamp-hour per gram. But if we want to have a lighter battery or longer electric vehicle driving range, we need to have a better material, which can give us a higher capacity, both per unit volume as well as per unit weight. So silicon came to us because silicon can provide a theoretic capacity of more than 3,000 milliamp-hour per gram, which is almost 10 times higher than graphite. Silicon also provides outstanding volumetric energy density as well. However, there are several challenges here for silicon electrodes prohibit the wide application for the current stage. The biggest issue is while providing 10 times higher of capacity than graphite, the volume change during the cycling will be very significant. For example, during the lithiation process, the volume will expand more than 300%. And during the following delithiation process, the volume will change back to the original shape, which is another about 300% in theory. So during this huge volume change, the surface stability of the silicon particle will become very poor, which causes a lot of electrolyte reduction, such as irreversible reactions, forming the solid-dry interface of SEI. And I will introduce SEI in the following pages. One step back, I will say why it is important. Because the cycling life is critical for lithium battery, especially for the automotive application. On the left side, there's a table shows the USABC battery performance goal. USABC stands for United States Advanced Battery Consortium. It is an organization provides some research advices as well as some research funding into the battery research community. And it is formed by the big three auto companies in the US. This set up those kind of battery performance goals, including the energy density, specific energy, as well as cost requirements, and more importantly here is the life requirements. For the battery used in the automotive application, the ideal calendar life will be more than 10 years, and the cycle life, which requires more than 1,000 cycles. On the right-hand side, it shows the percentage of capacity retention upon cycling for the first 100 cycles only. We can see that even for the 99% of the cycling efficiency, it's not sufficient for us to get enough capacity retention, even only for 100 cycles. There's a criteria of defining the battery failure for the automotive application. It's 80% of capacity retention. If you draw a line on the 80% of capacity retention, we can see that even 99.5 or 99.9% is not sufficient enough. That's why cycling efficiency is important. Cycling efficiency is highly related with the solid-dry interface. That is the topic we are interested in today. So a brief introduction about solid electrolyte interface or SEI. ICI is a passivation layer formed between the solid electrode and liquid electrolytes. It is composed by many different species, some organic species as well as some inorganic species. In order to study SEI, we want to answer a few questions, such as how does SEI evolve during the cycling, and which SEI components are desirable and or undesirable, how we can modify or control the SEI layer, and more importantly is how does mechanical deformation influence the SEI. In order to answer these questions, we need intensive effort both on the experiment model as well as modeling to study the SEI. one initial mechanics analysis can show some critical factors of the silicon electrodes, such as the size influence on the stability of the particles. Now, there are several mechanical models give us the size limit, give us how the SEI we want in the system, but more importantly, we need reliable material properties, such as silicon properties, lithiated silicon properties, and the SEI properties as the input for those models. As well as once we have the model, we want to have the experimental validation. That's why we have this important topic today for this webinar. And now I will move the presentation to Dr. Teddy Huang from Bruker, and he will introduce some experimental capabilities of studying the SEI.
Okay. So, Xiao, do I have the? Hold on a second. Okay, cool.
Go ahead and show your screen, Teddy. There we go.
Okay. Am I on now?
You are.
Okay, great. So let me show the cursor as well. Make sure that everyone can see it. Okay. Good morning, everyone. Of course, thanks Sarah and thanks Hector for the introduction, and thanks Dr. Ling for the great introduction about the importance of the battery research. So I'm here for my section. I'm here to introduce the technique that the primary techniques that we use for these studies. And we have used the atomic force microscopy, that is AFM, for these studies. So the way to examine the mechanical properties with AFM is through the so-called force distance curves. And because of this, we use the peak force tapping technique. So the peak force imaging is based on the real-time force captures of the force curves. And peak force tapping is sinusoidally modulated probe and of resonance low frequency. So it doesn't rely on the mechanical resonance, but it is a tapping mode. And the tapping frequency is typically 1 to 2 kilohertz for this study. So because of this physics, of this tapping mechanism, so it has many advantages. For example, it allows a stable and ultra-low imaging force. And this stable ultra-low imaging force is benefits high-resolution imaging. It also makes AFM very user-friendly. For example, no cantilever tuning is required as it doesn't rely on mechanical resonance. And this is very convenient for liquid imaging. As you know, a lot of in situ battery research is in liquid. And it also has a function called automatic image optimization. And this is really help new AFM user a lot because it frees AFM user from the tedious efforts of feedback parameter adjustment. And as an example, so on the right is a DNA helical structure, and this is observed in liquid using peak force tapping. And as you can see here, the peak force or the maximum imaging force for this example is only 49 piconewtons. And we can clearly see the double banded corrugation. And the inside image here shows the major and minor groups of DNA. Peak force tapping, since it performs a force curve at every tapping cycle. From this real-time force curve, from its analysis, quantitative nanomechanical imaging, and more importantly, at a normal AFM scan rate as possible, it is realized. And another feature of peak force tapping, because it's doing low-frequency tapping, and during each tapping cycle, it has a contact duration. For example, here from the snap contact to the break contact from B to D, it has a duration about 100 microseconds. So this is a magic. This is really a nice duration because it doesn't require a very fast electronics. For example, if you have a sensor circuit that has 10 to 20 kilohertz bandwidth, then you can effectively capture any electrical signal during the tip sample contact in this duration. So then it also provides a simultaneous nanoelectric measurement. And in this work, that Ravi is going to talk about, the primary technique we use is the AFM, or peak force electrochemical AFM. So it is AFM again based on the peak force tapping. So in this mode, the AFM performs the peak force imaging on a working electrochemical systems. So for this system, there is also a built-in heater, and we have a temperature control system, and this temperature control system allows ambient to 65 degrees C. And the EC cell, as you can see here, and Ravi is going to give you more detail on that. The EC cell is designed to be, of course, compatible with a wide range of electrochemistry. And another important feature is that during imaging, the cell closes up upon the tip engagement. This is very important, especially for lithium-ion battery study, because this is to avoid the evaporation and, of course, loss of the volatile solutions. Since the sample, for example, the silicon anode or the battery solution, they are very sensitive to air and water. So, of course, it naturally requires the ambient control. So for this, we integrate our AFM with the glovebox techniques. As you can see that the whole AFM is housed inside a glovebox. And this glovebox is capable of providing atmospheric isolation. And this isolation is by a controlled, non-reactive environment. And this is argon-filled. Argon-filled glovebox. It provides less than 1 ppm moisture and oxygen content environment. And today, I'm here also to introduce a new technique that Bruker launched not long before. And of course, I'm definitely going to show you some examples that related to lithium-ion battery research. And so this technique is peak force scanning electrochemical microscopy. It is an AFM-based SECM technique integrated with peak force tapping. Different from the AFM I just talked about, in peak force SECM, the nano-electrode probe, so the AFM probe is a nano-electrode, and this nano-electrode probe is part of the electrochemical system. So you can see that in this biopotential configuration, we have 4 electrodes, and the tip and the sample, they are both working electrodes sharing the same content reference electrodes. So combining with AFM, especially with the peak force tapping technology, peak force SECM is capable of capturing simultaneously a multimodal information such as topography, mechanics, conductivity, and electrochemistry. And because it's using a nanoelectrode, it allows the resolution, electrochemical resolution below 100 nanometer, and this is order of magnitude higher than the conventional SECM using micro tip. So the core technique of the peak force SECM is the nanoelectrode probe, because this is pretty much the most critical part of this technique. So here shows the pre-mounted nanoelectrode probe, and this probe is encapsulated in glass and sealed with chemical resistant epoxy. And as you can see here, the probe encapsulation, it was designed to have a relative large size, and this is for ease of handling. You can also see some groove on the glass housing here. And the most important part is the tip apex. So the tip apex has a platinum coated area of about 50 nanometer in end tip diameter, and with about 200 nanometer in tip height. Other than this electrochemically active region, the probe is fully insulated by dielectrics, mainly by a coating of silicon dioxide. With this design and packaging, current flows only through the tip apex and no leakage elsewhere. For this nanoelectrode probe, the components for assembling the nanoelectrode probe, including the glass and the epoxy, we have tested this component extensively for chemical compatibility in a wide range of liquids. And over 124-hour immersion into the liquids, as listed here, it shows less than 1% change in mass before and after the immersion. This liquid, as you can see here, includes aqueous base and acids, and some of these acids, for example, nitric acid and then hydrogen peroxide, they are strong oxidants. And of course, we definitely test them on organic solvent, especially those are frequently used in non-aqueous electrochemistry, for example, acetyl nitrite and many organic solvents that used for regular cleaning. And related to the topic today, we also test this component into solvent and solution for battery research. For example, all these DC, DMC, EMC that are well known for battery electrochemists. And we also test that. In 1 molar LPF in the ECDMC, that a solution that we actually use in this studies. So as a nanoelectrode, we also test its electrode its EC performance, and this is a cyclobutanogram of the probe in a ruthenium hexoamine solution, and the sigmoidal or the S shape of this curve is very typical for nanoelectrodes. And you can see here on the non-fluoridated region, it has a negligible leakage and capacitive current. So that demonstrates a very high quality insulative coating of this probe. And the probe design is robust for handling and electrochemically stable. We're showing 2 CV curves here. These 2 CV curves will result before and after a sequential handling and EC test. And this handling and EC test include, for example, 4 rinse and dry cycles, 5 minutes amperometry, and 29 CV cycles. And from the comparison here, no degradation on EC performance is observed. And here's another example, and this is the EC performance test in a ferrocyanide solution. And as you can see here, this is actually 50 continuously CV cycles that plotted together, and you will see no difference at all among these CV cycles. And indeed, before these CV scans, the sample has been tested for 3 hours of amperometrics measurement. As shown here, there's no performance drop observed at all. Of course, I mean, we get a CV curve, we got a tip current, but how do we know the tip current is from the very tip apex instead of somewhere leak? Then we go ahead to capture the approach curve, and of course the approach curve can also tell you the spatial sensitivity of the electrochemistry. And as you can see here, these are the approach curve, and this curve displays the relationship between the tip current and the tip sample distance. And the dashed line here, or the dotted line here, are the experimental results, and the symbol line here are the console simulation. So as you can see, our experimental results are very consistent with the console simulation. And more importantly, we can see that the change of the tip current occurs mostly within 100 nanometer of the tip sample distance. This is because the thickness of the diffusion layer, as you can see here, the diffusion layer thickness is less than 100 nanometer. Such a compact diffusion layer, and so that the high spatial sensitivity on this approach curve guarantee the sub-100 nanometer resolution in EC imaging. And this is the CV curve using another redox couple, which is a 10 millimolar ferrocene in 1 molar LPF in ECDMC. So this is a very typical lithium-ion battery solution. And it has been shown by the Truman group that ferrocene has an electrode potential of about 3.3 volt with respect to the lithium reference. And we have observed the same result. And here is a conductive AFM image of a silicon anode pattern on a copper current collector here. This measurement was done using the SECM nanoelectrode probe as a conductive AFM probe and inside a glovebox. And this is done actually in a dry environment, no liquid here. I just want to show you that, as you can see, right, on a amorphous silicon surface because of the native oxide, so you won't see any electrical current there. And we know that, and then this is oxide surface, it's inactive. So we use the same sample and then run the feedback mode in the of the SECM in this solution with the ferrocene here, and you can see that we get an approach curve, and the negative feedback is as expected on the silicon surface because this is inactive. Another example that related to battery research is the study of Hopg sample, because Hopg is a well-known electro material, and people would like to use it for lithium-ion battery study as a model system. And this study here is showing an example of a surface defect on an Hopg electrode, and this high-resolution image shows a submicron defect area. And this defect area is only about 0.4 nanometer higher than the surface terrace. And this defect results in 60 picoen, or as you can see here, more than 10% tip reduction. And very interestingly, this region also has a very different nanomechanics compared to the terrace. For example, the adhesion force is about 4 nanonewton less than that on the terrace. So this is actually one of the examples of the multimodal imaging from the PIC4 SECM. You can get topography, electrochemistry, and also nanomechanics. And as mentioned above, the probe design allows current only flows through the tip apex. And the insulation scheme also minimizes the strict capacitance and parasitic current. And this naturally enables the probe to be used in liquid in situ for nanoelectric study. And so here is an example of conductivity measurement based on PIC4 tapping mode using this nanoelectrode probe in a glovebox, of course, in liquid. And the liquid is the DMC. So this sample is a platinum electrode partially covered by the silicon nitride. And the conductivity map clearly differentiates the exposed platinum region here. We can use the point and shoot to capture the ivory curve at the location that we're interested in. And the ivory curve capture around these three locations, number 1, 2, 3, are shown on the left here. So as you can see here, number 1 is the most conductive, number 2 is less conductive, and number 3 is actually on the silicon nitride island, and we would not expect any meaningful current. And that is true. And the ivory curve here only shows like a few picoen, about 5 picoen background current. And this few picoen background current is very important. It demonstrates that we have a very good insulation scheme that allows you to do nanoelectric measurement in liquid. And for this technique, we have been collaborating with many research institutes around the world, actually. And we have successfully applied PIC4 SECM in a variety of studies. This application example lead to many publications that either has been published, has been submitted, or will be submitted soon. And for more detail, I would encourage you to watch our online recordings of 2 recent webinars that are specifically focused on PIC4 SECM. So now, let me move on to Ravi, and who is going to talk about our recent progress on the study of lithium-ion battery.
While we're going through this transfer, attendees, I want to encourage you to submit questions through your questions dialogue on the webinar interface. We're going to have a questions and answers session at the end of our Ravi's section. So I do encourage you, please submit your questions through the questions dialogue. Thank you.
Thank you, Teddy and Hector, for introduction and introducing all the AFM techniques and SECM, which is very useful for studying lithium-ion battery research. So now I will take over, and I would like to talk about how I have applied some of these techniques in studying SEI and some of its important properties. So I will be mainly talking about SEI and its morphology, mechanics, and electrochemistry from now. So at first, let's talk about how a lithium-ion battery works. So in a lithium-ion battery, there is like two, so one is cathode and one is anode. And what we are doing is like we are moving lithium from one of the electrodes to another while charging and discharging. But like during this process, the electrolyte is not stable, and in the voltage window that we cycle the battery. And due to this, the electrolyte goes through a reductive decomposition, and the product of this reductive decomposition starts depositing on the anode surface, which is what we call solid electrolyte interface layer. So now this layer acts as a passivation film, which is very important for the functioning of lithium-ion batteries, because this has to be electrically insulating, but it should be lithium-ion conducting, so that the lithium-ion battery is functioning, but it stops the further reduction of the electrolyte. So ACI stability is very important when we talk about lithium-ion batteries and its long-term cyclability. And given all the requirements of automotive industry that it has to go through more than 99.9% of cyclic efficiency, this is a very important step in achieving that. So the landscape of materials for lithium-ion batteries. So as Chini already talked about, people have been using graphite for a very long time, but its capacity is very low. And if we are talking about electrification of automotive industry, we need to find new materials which can give high capacity. And as you can see, like silicon falls in the anode materials in the far end, and it has almost 10 times capacity than graphite. So it is of a very, it has got significant interest in automotive industry and in all the universities to research on it, to use it in lithium-ion batteries. But as Chini talked, it comes with a lot of problems. One of the main problems is that its huge volume expansion and contraction, which results in surface instability. So if there is any kind of layer which is there on the surface, it is going to get through a lot of stress. So due to that stress, the ACI could get affected or damaged, and that is one of the big issues which could result in continuous degradation of the electrolyte and continuous ACI formation. So that is one of the main issues with silicon, which I am going to focus on. So in these next few slides, what I want to focus on is how does ACI layer fail? So there has been significant amount of research done in terms of chemistry of ACI, identifying what are the components, like chemical components of the ACI. But like my talk will mostly focus on mechanics of the ACI, that how does ACI layer fail? Does it crack, delaminate, or fall off? What are the mechanical properties of the ACI layer? Like what is its elastic modulus? What are the fracture toughness? And how can we tailor these properties so that it can withstand huge volume expansion and contraction of high capacity materials like silicon, so that it can be utilized commercially? So most of part of these questions have been answered, and like you can see some of the publications here which has been published recently. So I would like to first talk about what is the experimental approach that we need to use to answer part of these questions. So one thing, if we are talking about mechanics of the ACI layer, we need to use a model system so that we can apply a controlled strain to the ACI layer. And for that, what we have come up with is a patterned silicon island structure. So what you can see is that the sample geometry is, we have a quartz wafer, and we have the current collector, titanium and copper layer on top of that, and we have silicon islands fabricated through photolithography process. And so what happens is that during lithiation and delithiation, these islands go through huge volume expansion and contraction. But like now, what you can see is that there is a lateral stretching of the silicon while it is expanding. So if any layer is on the top of this silicon island, it will feel that stretch. So we are applying some kind of strain to the ACI layer and trying to see how the ACI layer behaves by applying these kind of mechanical strains to it. So this is our experimental approach, and it would be more clear if I go to the next slide. So what you can see is that when we have silicon, like as we are lithiating the island, first thing that happens is that the reductive decomposition of ACI of the electrolyte, which results in the ACI layer formation. Now, as we are keep going down in the voltage, there is going to be lithiation of silicon and it will expand. So as it is expanding in the lateral direction and in the vertical direction, it is applying some kind of strain to the ACI layer. And what we are looking for is that how does this strain affect the ACI? So would we be able to see cracking or delamination of the ACI layer? So my main approach is to use this kind of model system and use AFM technique to see what happens to the ACI layer or look for its properties. So Teddy showed you some of the AFM setup, but like what we are doing is like, this is one of my own cells which I built there. So what you can see is that there is two electrodes here. One is like one is our silicon island electrode, which you can see, and the lithium is on the top, just below the glass window, which is acting as both counter electrode and reference electrode. So what we do, so the whole results that I will be talking about in the next few slides is going to be in situ and operando. So during this whole operation, while we are lithiating and delithiating, we are constantly monitoring how the electrode is behaving. So we are monitoring its topography changes while it is lithiating and delithiating. So during this whole process, one important thing to note again is that the cell is closed. So no electrolyte is evaporating inside glove box. So it is like constantly stable inside a glove box. So let's talk about, I'll talk about some of the results that I get. So most of my islands, silicon islands, are like almost 200 nanometer thick and 15 by 15 micrometer in dimensions. So what you can see is that as I'm going through lithiation, there is significant amount of expansion both laterally and vertically. Most of the expansion is vertically, but there is a lateral expansion of these electrodes at the edges of these islands. And because of that, what you start seeing is that some kind of cracking which starts appearing in this like edge and corner zones. So I'll talk later like why it is happening mostly in the these corner and edge zones. But what you can see is that as we lithiated, there is some appearance of like nano and micro cracks at the edge and corners of these islands, which is and when we delithiated, these cracks kind of close up, and there is some kind of delamination also results. As we keep lithiating and delithiating, the cracks become more wider and they open up more further. So there is a dynamic evolution of these ACI cracks. And one thing to note here again is that these whole cycling was done like with voltage holds. So you can see in the bottom left corner is that the EC, electrochemistry of this cell is given. So we use 0.6 volt hold, and then we go to lower voltages and hold till lithiation is complete, and then we delithiate, and then follow it for next few cycles. For this study, we have used electrolyte, which is EC-DC and 1M LiPF6. So one thing of main interest here is that the lateral sliding of these islands, because this sliding of this island is what putting the strain in the ACI layer. So what you can see is that this strain is almost of the measure of like 1 to 1.5 micrometer, which results in like 10% expansion, 10% lateral expansion of the whole island size. So if we go and take a closer look at the ACI cracking, so what you can see is that at the corner of the island, as we are in OCV, like there is this kind of profile, and you can see both the topography and the height profile on the red. So as we lithiating, there is an opening of these cracks, and the cracks run very deep into the ACI. And once we delithiate, there is like a contraction of this ACI layer along with the underlying silicon, which leads to both partial closure of these cracks, but there is partial delamination also. So what you can see, two things to note here is that the cracks which form in the ACI layer, they don't fill up with new decomposition products. which has been long postulated in lithium-ion battery research publications, but has never been really seen. So this is really the first ever observation of real-time cracking of the SEI layer, and what happens after it cracks. So the cracks don't fill up completely. There might be a possibility that the cracks only fill at the bottom of these cracks, which is very hard to see because of some of the problems associated with the tip geometry and how far it can reach in the crack. But given all that, the cracks don't completely close up. And you see the white region surrounding these cracks, that is just telling that the height is higher there, which means that there is a partial delamination which is happening at the silicon and SEI interface. So there is cracking of SEI layer, and as it cracks, there is partial delamination, which also results. So if we look at the edge sites, the cracking is less severe compared to the corner sites, because at the corners of these islands, the island is going through almost like 3D deformation. So both X and Y and G deformation, but like in the edge region, it is almost going through 2D deformation. So the deformation is less severe compared to the corner. But what you can see is that still there is cracking of the SEI layer in this S region, and while we delithiate, there is pile of this material or like partial delamination. Again, these cracks don't even fill up at these sites. So two things to get out from these two slides is that the cracks, once they form, they don't completely fill up with new decomposition products, and we can in situ and operando monitor these crack formation by applying these AFM technique from Bruker. So one thing that I want to mention here very carefully is that these cracks are not coming from underlying silicon, because while we are lithiating silicon, the lithiated silicon is at compressive stress. So any crack would not form in the underlying silicon. But like because of the stretching of the SEI layer, the SEI layer is in tensile stress mode, and that's why it is resulting into tensile strain and cracking of the SEI layer. So to make this point more clearer, after cycling, we did some ex situ fib cross sections of these cycled islands, and what you can see is that these cracks of the SEI is mainly focused on the edge regions or the corner regions of the island, and you can also clearly see the partial delamination, interfacial delamination of the SEI layer. So it is very clear, and you can see that the silicon is in complete silicon. There is no cracking, although there is partial debonding of silicon in the edge region, but it is not getting cracked. So it is, the cracking is mainly limited in the SEI layer. So another thing that we observed is that as we start lithiating, the cracks start appearing in the edge and corner regions, and these same cracks keep evolving further. So what you could see is that in the first cycle at 0.05 volt, there is some cracks appearing in the edge and corner sides, but these same cracks evolve further as we go to the second cycle lithiation 0.05 volt. So there is the same cracks which form initially, open up and kind of close again. So this also proves the point that these cracks, these SEI cracks don't fill up with new decomposition products. So they remain open in some form of nanochannel cracks, which we could study with AFM. So another thing which is very clear from this height profile and these AFM surface topographs is, if I take a diagonal cross section and plot the height profile, what you can see is that first of all the cracking behavior, and there is some kind of surface SEI lifting. So what you can see is that these edge sides, which show like some kind of white height behavior, white color, is like lifted. So there is both cracking and delamination sections which are present here. So what happens after you keep cycling further and further these islands? So one thing that is happening is that once you have already cracked and partially delaminated the ACI layer from the underlying silicon, due to cycling fatigue, it can also spall off. And that is what we can see here is part of the ACI from underlying silicon has already spalled off. And only the center part, which is not going through any tensile strain, remains there as it is. So what you could see is that in the topography and modulus sections channels, the sites which are going to delaminated or spalled off later during the cycling have like a very small modulus. That is, when we are imaging the electrode, they are not very well attached to the underlying silicon, so they come off. So if you see the first two images and the later two images, part of the ACI has already spalled off, which can be clearly seen through this AFM technique. Now, so like what we have seen, till now what we have seen is how ACI layer behaves when you apply some kind of strain to it. So we saw that there is cracking and delamination of the ACI layer. So that is very important property of the ACI layer when people are building these mechanical models of these ACI layer and cyclic aging of these electrodes. One important thing which is missing right now is some kind of elastic modulus measurement, or which would be useful in predicting some of the other important properties of the ACI layer. So from now, what I will be talking about is quantitative nanomechanical mapping, which is called QNM of ACI layer, to study some of the elastic properties. So as Teddy already introduced some of the PFQNM, what we can do is that by applying some kind of force to the ACI layer, we can get these approach and retract curves, and by fitting appropriate models to this retract curves, we can get some kind of elastic modulus values for the ACI samples. So one important thing in ACI is that how do you control the ACI to withstand like these huge volume expansion and contraction. So what you want the ACI layer is to be like soft material so that it can stretch and come back, stretch and come back. So it should not be stiff. So one thing that I tried was that if by controlling the formation cycle in the very first cycle, we can control the ACI thickness or how the ACI is forming. Like if I'm going through like very high voltage, like 0.6 volt hold, it will be mostly organic, versus if I'm going very low voltages directly, it will form mostly inorganic components. So that's what we did here, and what you can see is that thin ACI sample, when I say it is formed at lower potentials, and thick ACI sample is like when it was held at higher potentials, like 0.6 volt. And what you can see is that there is a clear difference in the kind of elastic modulus you can measure. So clearly, the very stiff ACI is not going to be working very fine because it will be more brittle compared to the softer one. And all these measurements were done inside liquid. So these measurements are reported from the liquid environment. So what you can see is there is a DMT modulus of almost 2 GPa of the ACI on the thick ACI sample. So what we guess is that this number is reporting mostly of the organic character of the ACI on the top surface. And thin ACI sample, this is giving some of the inorganic character of the ACI layer, which is more hard compared to the more organic character of the ACI. So another thing to note in PFQNM measurements is that you have to make sure that the measurements are right. Now, how do we make sure that the measurements we are doing are right and it is reporting right modulus numbers? So Bruker also has some kind of known modulus samples like polystyrene with some kind of LDPE bend, which is known to, so polystyrene is known to have some kind of 2.7 GPa for polystyrene as modulus. So what you do is like you reference the tip, like, or you calibrate the tip from these kind of samples and you measure the elastic modulus on these kind of samples. And once we did that with a force of almost 200 nanonewton, and indenting it for like kind of 1 nanometer or so, we get this 2.9 to 3 GPa measurement of the polystyrene sample. So we kind of sure that if we get some kind of deformation in this range, our modulus numbers will be like 2.7 GPa. So now if we go back and do the ACI samples measurement, we will have some kind of surety that, okay, the measurements are right or whether something is going wrong. So I will come to the conclusion slide with this, and we have demonstrated a new approach for applying controlled strains to the ACI films with patterned silicon electrodes. And extensive cracking of the ACI layer was observed during lithiation, where the ACI film is subjected to tensile strains. And an important observation was that these ACI cracks don't fill up with new decomposition products, and they remain open. Also, we use PFQNM to measure the elastic modulus values and could verify that the top layer is softer compared to the inner layers, which has more inorganic characters. And at last, Bruker AFMs with peak force tapping mode provides a versatile solution for lithium-ion battery research. So most of the results I have presented today has already been published in this paper, which is at the bottom of this page. And at last, I would like to acknowledge General Motors R&D, Bruker, and Brown University for funding and funding this research, and mainly Bruker for me to come in and do these kind of experiments, which is very useful. And I would also like to thank my advisor, Dr. Brian Sheldon, Anton Tokarno, who helped me doing some of these measurements, Peter, Xingcheng, and Ivan from Bruker, who helped me in the Bruker during this whole experimental process. And at last, DOE, US DOE, BMR funding for funding this project. Thank you.
Thank you, Ravi. We appreciate that and appreciate all the attendees staying on and listening. We did receive a few questions. I'm not sure that we're going to have time to address them all, but be assured that if you did register and you have a question, we will follow up with an answer. So let me go. We have about 6, 7 questions. This one seems to be for Teddy. How does the resolution, for example, current, height of the tip behave with time? For example, its stability, does it change much?
So let's talk about the resolution first, right? I showed you the theoretical simulation showing the compact diffusion layer. It's the thickness. I mean, actually, it's less than 100 nanometer, or you can even say it's 50 nanometer. So it has the possibility to achieve about 50 nanometer resolution, and we did see that from our experiment. But normally, I have several examples showing that it has a resolution less than 100 nanometer. And if you're interested, you can go to read the paper that we just published on Microscopy today. And I believe later this year or early next year, we're going to have more paper coming out, and then they're showing small example about high resolution electrochemical imaging. So now we're just saying that we can achieve resolution less than 100 nanometer. As for the the height, and as you can see that, right, the tip height of the active platinum electrode is 200 nanometer, and below that is actually it's a 200 to 300 nanometer. It depends on the accuracy of the focus ion beam. Then below that is actually a shoulder. It's actually the piece, the coating layer. So if your sample surface is too rough, for example, like a more than 250 nanometer, it's going to be challenging because the tip even cannot touch the bottom. So that's one of the limitations. Stability, I just showed you several examples as the slide that Ravi showed here. We can do like 100 CV cycle. We do 3 hours amperometrics measurement, and you can see that the tip is really stable. And we have customers that can use the same tip for more than a week, and then they use them daily. So the tip is actually quite robust. Because for nano electrode, the well-known issue is actually not the performance itself, it's actually the handling. Most of the time, you need to be careful with electrostatic discharge, more like a handling. Of course, I mean, I don't want to take too much time. We can talk about it offline. Yeah, just send me email, and then we can continue.
Okay, thank you, Dr. Huang. The next question, let's take the short question here. Seems that it's for Ravi or Dr. Zhang. Can you tell us why you use nickel wires to connect to lithium?
So one thing that I would say is that we could have used also copper. So there is no particular choice. But one thing that I have noticed through my experiment is copper has more lithium solubility compared to nickel. So the side losses happening to the nickel is less compared to other wires, let's say copper. We cannot use other wires like, let's say, aluminum, because aluminum is also going to lithiate and delithiate. So we try to find a wire or a material which is less, which has much less solubility of lithium. That's why we used nickel wire in these experiments.
So on that note, let's go to another question. I think this is for Ravi again. How much lithiation are you talking about in these images?
Okay, so we are going to almost like 250% expansion and contraction. So we are talking about almost 2100 milliamp hour per gram of silicon. So it is lithium 2.2 silicon.
Very good. Thank you, Ravi. This next question seems to be for Teddy. What are the benefits of using peak force mode instead of contact or tapping mode in AFM SECM?
Well, so for the peak force tapping, I mean, the most straightforward answer is that, well, it will provide multimodal information, because as I showed you, right, peak force tapping can simultaneously provide nanomechanics measurement, and also because the special for electrode scheme of the by potential configuration of SECM, it can also provide a conductivity measurement. And if you want to talk about deeper, it's actually, for example, if you run on tapping mode is not convenient for liquid imaging because it relies on mechanical resonance. I mean, anything change, for example, temperature or even the volume of the solution change, it will shift your resonance and then cause some instability issue. Anyway, it's not very straightforward. And contact mode, because SECM, for example, for peak force SECM here, we run on something called interleaf mode. So it has an interleaf scan. You take the main scan to capture topography and other AFM information. Then in the leaf scan, lead the tip up, follow the surface topography to get the electrochemistry. If you run on contact mode, there's a problem, because on contact mode, the tip in the main scan during the topography imaging is constantly shorting with the sample, and it causes a lot of problems. It's more about like electrical protection. And of course, other advantages I already mentioned as the common advantage from the peak force tapping. For example, minimal shear force compared to contact mode, small force control, stable force control. So something like that.
Thank you, Dr. Huang. We're past 9 o'clock, but I do want to be fair. I'm going to have one more question, and this is for Ravi. I think it's important to address. A lot of previous papers have reported much thinner SEI. However, the thickness reported here is on the order of 250 to 300 nanometers, which is questionable. Ravi, can you address that, and we'll have that as our final answer.
Yes. So one thing that I want to mention is that SEI thickness is very dependent on what kind of electrolyte people use and what kind of cycling conditions you are using to cycle the battery, which has been already published also from our group, showing that different cycling conditions can result in very different SEI thicknesses. So one thing that I want to mention here is that in our electrochemistry cycling that we have done, we have hold the electrode at 0.6 volt for 1 hour, and we can watch that the SEI is keep building during that time, and that's why we have like higher thickness. One another thing is that there is another paper from Army Research Lab which talks about thicker SEIs. So there are different papers which talk about there is thin SEI versus thick SEI. So I would not say that all the literature is talking about thin SEI, but there is both thick SEI and thin SEI is present in the literature. So I cannot really comment that why my SEI is like 250 nanometer, but like one of the main things is that in ex situ studies, there could be a problem of some kind of washing off the top organic layer, which could result in low thickness of the SEI.
Thank you, Ravi. I appreciate your responses to all the speakers, and thank you for the attendees. We do have additional questions. We will address them with you offline and via email. And thank you again for participating. We appreciate our presenters as well.